Hello everyone, I hope all of you are doing really well. So first of all, welcome to Chemistry at your fingertips. Now this is the second chapter for the ASD board exam series, which I'm going to discuss over here. Okay, so the second chapter is nothing but alcohol, phenols and ether, which is basically from the organic section. And if you could see here, again I have divided this chapter into subparts so that the video is not too much lengthy and you can actually study those questions in different sections as well. Okay, so this is going to be the part number one, wherein we'll be discussing few questions and maybe few MCQs as well. Okay, so now let's see what exactly could be the revision strategy. Now, as the name suggests, alcohol, phenols and ethers. So alcohol is going to be the biggest part of this particular chapter, and then followed by phenols, which will be little bit smaller, or you can say comparatively smaller than alcohols. Then in ethers you have very little to study, right? So when it comes to board exam point of view, the questions, you could see the questions are pretty much simple to understand. So I would recommend that when you're preparing for this chapter for revision or maybe for your regular studies, you divide it into three parts. Okay, of course when you're studying for the first time you have to do everything, but I guess by the time you'll be watching the video you might already have studied a lot about it, right? So part one, alcohols, you could just focus on the preparation, and you could just if you have a pen and paper, you could just make a notes for whatever I'm speaking right now. Okay, so you could just write down the dehydration reactions and all. Now when it comes to preparations are pretty much simple to understand, but just pay more attention to the Grignard reactions. Okay, so preparation using the Grignard route, that is very important. Okay, so Grignard route is very important. And then you could have hydroboration, right? Hydroboration reaction. So just try to do that and the remaining part as well, right? Oxidation reductions, I think those things you already know, but these Grignard and hydroboration, they are a little bit tricky to understand. Okay, just try to understand the essence of these things. Grignard reagent, you can prepare what types of alcohol and what could be the reactants that you could use. Now if you have attended my lectures or if you already have an access to my videos, you might be knowing about the shortcuts, okay, for Grignard reagent and even the hydroboration as well. So okay, you can just watch those on my channel, or if you are interested you can just write an email, I'll give you the video access. Okay, then comes the oxidation and reduction, not reduction, oxidation and dehydration reactions of alcohols, and few name reactions. If you want you can do it, right? Now let's come to phenols. There is one method of preparation using benzene sulfonic acid. Okay, so that you try to do it, and because that's one of the questions that keep on appearing in your board exam. And then you have reactions of phenol, bromination, and 2,4,6 trinitrophenol, that is picric acid preparation. I think you should do it as well, right? And I think reactions of phenol are pretty much simple to understand, so I don't think there'll be any problem. Now when it comes to ether, Williamson's ether synthesis is important. And then you have reactions of concentrated reactions of ether, that is simple ether and mixed ether, using cold and hot HI. Now that's something which is very important, right? So I think that's it. If you would like to know what could be the time you could devote it for the chapter, so let's say if you're doing the revision, you can just devote 45 minutes for alcohols, 30 minutes for phenols, and maybe 15 minutes for ethers, if you are completely thorough with the topic and if you want to do this revision. By doing revision, I don't mean that you can keep on writing things. I just want you to do things orally, because anyway you are going to write these when you are solving the questions as well, right? But anyway, you have your own strategy, but I would recommend doing these three chapters, not on one, doing these three sections not on one day, right? You can do part one today, you can do part two tomorrow, you can do part three, which is ethers, on maybe day after tomorrow, right? So do this on 3 different days, so that you'll be pretty much relaxed and you'll get a lot of examples to practice as well, right? So now let's begin without wasting much time. Okay, so before I begin the video, if you really like this video, please hit the like button. Please hit the like button, and if you would like to receive more updates, then please hit the subscribe button and do not forget to press the bell icon. Yes. Okay, so guys, this is the first reaction. Okay, so this is the first reaction that we are going to discuss, which is the best reagent for carrying out the following conversion. So if you could see here, so the conversion is something like this. This double bond is getting converted into a single bond and there is an OH, right? So the only way is addition reaction, right? Addition reaction. So if you could see here, option B is going to go off. Now this is reduction, right? So this is basically reduction, and by doing reduction you can only introduce hydrogen. So this is going to be out of choice. This is going to be out of choice again. This is reduction. So the only possible option is basically option D, which is nothing but using diborane, B2H6 H2O2, right, in a basic medium. So how you could do this? Now this is a very simple way to do. So you have a CH3 over here, correct? And then this double bond can get converted into a single bond. So you already know the hydroboration is nothing but anti-Markovnikov's. Okay, this is anti-Markovnikov's water addition, right? So when you write anti-Markovnikov's water addition, this is H plus and OH minus, right? So you have H plus and OH minus. So here there are no hydrogen, here there is one hydrogen. So OH is going to go over here, right? And this is basically the product, correct? So it's pretty much evident. Now what's the correct answer? The correct answer is obviously option D. Okay. Now let's move on to the next part, which is the most resistant alcohol towards the oxidation reaction. Okay, now oxidation reaction. So this is pretty much easy to understand. Tertiary alcohols are highly susceptible due to their steric hindrance. Okay, so the correct answer is tertiary alcohol. So if you could see here, this is a primary alcohol and this is a secondary alcohol, right? So because this is attached to one hydrogen and two alkyl groups, and then if you could see here, this is the tertiary alcohol, and again this is the secondary alcohol, right? Yeah, this is attached to two carbons. So the correct answer is option C. So let me just write it down. So the correct answer to this particular question is option C, because what is the order of reactivity? So this is primary, and then you have a secondary, and then you have a tertiary. And why does this actually happen? Tertiary alcohols initially undergo dehydration reaction using H2SO4, resulting into the formation of an alkene, right? So I think this is pretty much simple to understand, and I think you might have already got this because it's just an MCQ, right? Okay, so let's move on to the next part. Then you have resorcinol. Okay, so let's first write down what exactly is resorcinol. So resorcinol is nothing but benzene ring in which there are two OH groups, right? And then they are meta with respect to each other. So on distillation with zinc dust, what exactly happens is that it undergoes oxidation. It undergoes reduction, right? It undergoes reduction. That means removal of these two oxygens, and as a result of which you get benzene. Pretty much simple, correct? So in this case, you get benzene. So it's pretty much evident that the correct answer is obviously B. That's basically benzene. Okay. Now, anisole on heating with concentrated HI. Now, this is little bit tricky. The reason behind this is, only the mechanism is going to actually help you over here. But anyway, this question is pretty much frequent, and it has already been asked in many of the entrance exam as well. So you have anisole, which is OCH3, correct? Now, on treatment with HI, that means initial step is basically the protonation of the oxygen which is attached to benzene ring, as a result of which you get a protonated anisole, correct? So you will be having O with a CH3 here, correct? And then there is going to be an H with one lone pair and a positive charge. Now, this I minus is going to have an SN2 attack over here, as a result of which I minus is going to attack CH3, and then you'll be getting CH3I plus phenol. Okay. plus phenol. So this is basically the correct answer. And the question is, why is it attacking the alkyl group? Why not the benzene carbon? And the reason is, this is already, you can say there is less steric hindrance because, it is SN2 attack, right? SN2 attack. Now there is one more reason. The reason is pretty much simple. So let's say if the I minus has to attack the benzene carbon, that means it should be positive, right? And this you already know, this is unstable. Phenyl carbocation is unstable, right? So this is basically the reason why it does not attack the benzene ring. So I think the answer we have to focus right now. So anisole on heating with concentrated HI is going to give us iodobenzene. No, that's not possible. Phenol methanol, not possible. And then you will be having phenol and iodomethane. Okay, so the correct answer is obviously option C. Okay, which of the following is the least acidic compound? Okay, so we already know about this particular thing. When we talk about phenols, okay, so phenols are acidic due to the resonance stabilization of the phenoxide ion, right? So let's say this is phenol and then you have a phenoxide ion over here, right? So this phenoxide ion is stable due to resonance, correct? So we can actually say this is stable due to resonance, correct? So this is acid, right? And this is the conjugate base. Conjugate base is basically stable, so the equilibrium is pushed towards this particular direction. Now, let's try to put the groups over here. So let's say if I'm having a group R, okay, and this R group could be plus I or minus I. So what is this plus I group going to do? This plus I group is going to donate electrons, right? If it is going to donate electron, it's going to increase the electron density. So you already know the charge is going to increase, right? When the charge increases, the stability decreases, correct? So when the stability decreases, that means the acidity, right? Acidity also decreases. So here actually the demand of the question is least acidic. Least acidic means it should have a plus I groups, right? So if you could see here, this NO2 is minus I, this NO2 is minus I, and there is no minus or plus I. So can you see these alkyl groups are plus I groups and they just donate electron, right? So that means option B is the correct answer, right? So this is going to be the least acidic. Okay, so the correct answer to this particular question is option B. Okay, now the next part. The compound incapable of hydrogen bonding with water is what? Okay, so here they are asking something which relates to the incapability of hydrogen bonding, right? So hydrogen bonding is possible whenever there is a heteroatom, okay, heteroatom which is more electronegative, mainly oxygen, then you have nitrogen, then you have fluorine and so on, right? So if you could see here, with water it can have, this particular compound can have hydrogen bonding with water. So water is going to be HOH, right? So there could be hydrogen bonding over here. Here also there could be hydrogen bonding. Here also there could be hydrogen bonding. So the only option that does not contain any heteroatom is option B, right? So the correct answer is option B. Now, these being MCQs, you are not supposed to take too much time in deciding. So it's pretty much evident from the options itself that the correct answer is option B, right? So the correct answer to this particular question, let me change the color. I think that's the best way. So the correct answer to this particular question is option B. Okay. Now the next is ethers react with, you have this keyword cold and concentrated H2SO4, right? Cold and concentrated H2SO4. So what exactly could be the answer? So you have CH3 and then there is this O, there is this CH3. Now this is going to react with H2SO4, correct? Cold and concentrated H2SO4, as a result of which initial step is going to be protonation. So you have CH3O, CH3, correct? And there is going to be H and then the next is going to be CH3. Okay, so now if you could see here, water is going to attack over here, correct? Water is going to attack over here, and as a result of which you will be getting CH3OH plus CH3, and then there is going to be O with one H with one H and a positive charge, right? So what happens? There will be deprotonation happening, and as a result of which you will be getting alcohols. Okay, so it forms oxonium salt initially, but then it gets converted into alcohol, right? So this is basically the correct answer. So let me just put this over here. So the correct answer is alcohol. The intermediate is oxonium salt. That I agree. Okay. Now the next one is hydroboration oxidation of propene gives what? Okay, so we already know this is nothing but anti-Markovnikov water addition, right? Anti-Markovnikov water addition. So you are simply supposed to add water in an anti-Markovnikov fashion, right? So let's first do this. So I'm going to write here B2H6. So what happens over here is you get CH3, simple way, CH2, correct, and then you have a CH2. So what we are going to do is look here. So you have BH3, you can write it as BH2H. Now this hydrogen is going to have a hydride character. So this hydrogen is going to go to that carbon containing a less number of hydrogen, right? So you will be getting something like this, and then what I'm going to write is 3 times, because you will be taking 3 moles of this, and I'm going to write a B over here, and then this will undergo oxidation, right? This will undergo oxidation, as a result of which you will be getting CH3, CH2, CH2OH, right? So the detailed mechanism you can actually find in one of the videos of my channel. Okay, you can also refer the Udemy videos which I have it for this particular topic for getting a detailed explanation about all the important reactions. Okay. So now the next part is write down the IUPAC name of the alcohol having formula C4H10O. Okay, now the key word over here is it is resistant towards oxidation. So the only alcohol that is resistant towards oxidation is 3-degree alcohol, right? So we are supposed to write down the 3-degree alcohol. So I'm going to write C over here. I'm going to write a CH3 over here. I'm going to write one more CH3 over here, one more CH3 over here, and then there is going to be OH, right? So let's write down the IUPAC name 1, 2, 3. So this is going to be 2-methyl propan 2-all, right? So this is basically the IUPAC name of this particular alcohol, and again to be very sure this is going to be a 3-degree alcohol. Okay, so I think this is pretty much simple question. I think, yeah. Now the next is optically active alcohol having molecular formula C4H10O. Now this is pretty much simple. Okay, now let's try to write down the different alcohols. So if you could see here, this is one alcohol, right? And can you see that this is not chiral, correct? This is not chiral. I'm not putting the hydrogens because you already know that there are hydrogens on every carbon. Now the next one is something like this. You have CH3 over here, and then there is this CH3 over here, then there is this CH3 over here. This is again not chiral, right? Now let me write down one more CH3, then I have a C, there is an OH over here, correct, and there is an H over here, and I have something like this CH2 CH3. So can you see this here? This is different, this is different, this is different, and this is different. So this is basically a chiral alcohol, and when it is chiral, this is going to be optically active, right? Very simple, optically active. So this is basically the structure. This is nothing but butan 2-all, right? So I'm going to write butan 2-all. Very simple and very easy. Let me just put this in a block so that you could understand it very well. Okay, so I think the questions are pretty much simple from the end of the textbook ones. Okay, so I guess this basically finishes the part one of the video. Okay, in the next part we'll be discussing more synthetic conversions and certain theoretical questions as well. Okay, so this brings us to the end of the video. If you like this video, please hit the like button and make sure you subscribe, and please press the bell icon to get periodic updates about the remaining parts. Okay, so I think that's it. I hope you have enjoyed watching the video. Thank you very much.